So I was thinking that in the light of current events, it will be an interesting break of the routine for those of you who are taking my classes and anyone else watching this to think about some way to analyze this question of whether a public policy with respect to intervening in the control of an infectious disease. So whether this policy actually is designed to serve the individual or the society at large. Because although this might sound a little bit controversial actually, because some people might think that I'm trying to basically prove that you shouldn't follow public policy. My point is to show actually with a little math exercise. It's not going to be a realistic model for real life diseases, but just a textbook exercise that there's a distinction between what is actually important or what's good for the individual versus what's good for the society. Now, most of the time, these two things overlap, but not always. And I think it's important to not lose this distinction. And educated individuals should basically always balance the two. It's not basically the idea that one should, doubt any public policy that is recommended or implemented, but it should be checked against the interest of the individual. And ideally, the individual should basically figure out his or her own path, so to speak. And I'll be more specific, although I can actually give already a quick example before I get back to the topic of this video with the math you see here on the screen already. So most people know that there are medical recommendations for various checkups. For example, one should do, let's say, a colonoscopy to screen for colon cancer starting at 50 years old and later. So the 50 years old is the cutoff for the first checkup. Now, that's not because cancer of colon doesn't appear below 50, but, the experts will make an analysis that, unfortunately, and however uncomfortable it sounds, is based, among other things, also on the costs and the finite resources, right? So, one cannot do every single type of medical checkup. There are probably hundreds of them for every single individual in a country. So therefore, whatever the decision is made, so whatever the recommendation is made, has to include an assessment of finite resources and how those resources can prevent as many diseases as possible. But for example, the question is, should one do a colonoscopy before you're 50? So, earlier than the recommended case, that is the time which one as an individual should decide for himself or herself. And, whether you can find funds to do that because the insurance probably won't pay, whatever. These are extra discussions. So the point is, the answer is not necessarily no or yes, right? Because one should basically always keep in mind that all of these recommendations have the society as a whole in mind and not necessarily the individual. But without enough with this digression. So let's go back a little bit to the math part. I should mention here that if you want more details on the math, because I'm going to skip lots of details in this video, you should watch the video in the description that I provide for this video. And those of you who took or are taking differential equations with me, you should know that all you need essentially, as soon as you understand how this how this model is implemented here, all you need is a separation of variables actually to do the math. For what I'm going to do in this video, I'll just focus on explaining the terms and writing down the main result side by side. So here's the story. Suppose there is an infectious disease in a population, and let's say the government, for one reason or another, can only implement one policy. Let's say, and again, this is not realistic, right? This is just a theoretical textbook example. So the government can only buy vaccination programs, so that people are vaccinated, or treatment. And let's say this is a disease that provides complete immunity. So once you get the disease, you either, whether you're vaccinated or treated, there's no reinfection whatsoever. So you have basically three classes of individual. This is the famous SIR model with some modifications. We have the susceptible class, which is the people who can be infected, that are healthy for now. The infected class, And in this case, in some models, this is called the recovered class, but I'm going to call it vaccinated class on the left panel. Because here the only intervention of the disease is that there's some vaccination. So there's a transition from S to I. So that's the infection term. Lambda is the infection rate. For those of you who are not familiar with epidemic models, lots of Greek letters are used to denote various terms. And V is the vaccination rate. So it's the transition between susceptible and vaccinated. So those people won't get the disease at all. And again, all the other relevant parameters are stripped away. So that's why I'm saying it's not realistic. So notice there's no disease, there's no death from the disease, right? I mean, nobody dies from the disease, just to keep the number of terms as few as possible, basically. So this is the time when you want to pause and you do the math, or if you want to see how the math is done. You can watch the video in the link provided below. For something similar, I mean, it's not exactly the same model, but the main idea is really the same. So one can prove, if you have some calculus background, you can actually kind of tell why that's the case. One can prove that in this case, the limit of S of t as t goes to infinity, so the size of the susceptible class in the long run is going to be 0. Because the infection will take place as long as you have infected people in the population, but the vaccination continues, so eventually all the susceptible disappear. Some of them will be infected, some of them will be vaccinated. The question is, how many infected eventually? Okay, so how can we, I mean, what's the final number of the final size of the epidemic, so to speak? How many people will get sick eventually? And one can prove that, so by integrating these systems, we can pair S and I, and you can do some separation of variables. One can show that the final size of the infected class of I of t, so that's basically the infected at time t, I of t. So the final size, that is to say the limit as t goes to infinity of the infected class, will satisfy the following equation, which is not an equation that you can solve by hand. And so you can trust me about the answer. I'm going to show you on the second part of the video the solution of this equation with Wolfram alpha, because this cannot be done by hand. I equals V over lambda ln of I naught plus over I plus S naught plus I naught. So the meaning of S naught, I naught, R naught, these are the initial population sizes. So the initial population of susceptible, infected, and recovered. So this is the equation satisfied by these terms. All right, so let's take an example. Let's say the vaccination rate is 0.02. So this has to do, let's say, with how much money the government has to implement the vaccination. So that's the vaccination rate. The infection rate is dependent on the disease and the way it interacts with the population. Let's say it's 0.0003. And let's say initially we have 2 infected individuals and then 100 susceptible. And let's say initially we don't have any recovered, because that's for later once the vaccination takes place. So this is kind of the situation at the beginning of an epidemic when you have just few infected people, like patient 0 if you want, and lots of people susceptible. And then the infection runs its course, and then all we do when we solve this equation for I, we figure out the final size of the epidemic, of the infected class. So this is what I'm going to show you in the second part with Wolfram alpha. So if we plug in our data in the equation, plus 102, right, 100 plus 2, and we solve, we're going to get I approximately equal to 8.17, which means that I will be 8 people. So 8 people infected eventually, which is pretty good if you think about it, right? From 100 infectious people. So now let's actually go back to the treatment policy. let's say we have pretty much everything else the same, except now the government doesn't buy vaccinations, but let's say buys a drug. Let's say for price reasons, whatever, right? I mean, like I said, there are two options: vaccination policy, treatment policy. Let's say that actually the burden in terms of money is the same, like everything the same except the fact that this is not a vaccine, but it's treatment. So you see, mathematically, the difference is that now there's a transition just from infected to recover. That's why I'm going to call now the R class treated people. So there's a transition from susceptible to infected, and then later on from infected to recovered via treatment. Okay, let's call that treatment. Although, again, remember, in reality, it could be also natural recovery, but let's imagine that these are the only way to control the disease. Like I said, either vaccination or treatment. Again, we can do a similar math, which I'm going to skip for now, but notice that, again, intuitively, in fact, we can tell that the limit, in this case of I of t, as t goes to infinity, goes to 0. We can debate discuss a little bit more why that's the case, but I'm not going to do it right now. This discussion is done in a different video. And so eventually I goes to 0 because, again, there's some transition from S to I as long as the infection takes place. But even if after the infection basically slows down, the treatment continues, so that eventually depletes the infected class. So now the infected class eventually goes to 0 because of the treatment. So you're left essentially in the end just with S and R. Now, one thing to keep in mind, which is very important, as t goes to infinity, so once the infected class goes to 0, R represents the infected people who are recovered because of the treatment. And the final size of S will be essentially those who didn't get the infection in the first place. So it's important to understand now, when I compute R, when we're done with computing R, that represents, again, all the people who are infected in the end, who are infected and then later recover, because everybody is recovered eventually in this model because of the treatment. So doing this a similar math like before, we can actually end up with an equation in S. So equation for the final size of the susceptible class. And it's kind of similar like the one before. It will satisfy the equation S equals R, the treatment rate, over lambda natural log of S over S naught. And then plus S naught plus I naught. And let's keep the initial size of these population the same as before. 100 susceptible to infected initially. And let's again plug in the same data as before. So let's say the treatment rate is the same as the vaccination rate, which is 0.02 divided by lambda, which is 0.0003, natural log of S over S naught. Okay, S naught is 100, and again S naught plus Y naught is 102. Once again, we can use the Wolfram alpha or something similar to solve this. So we solve for S, and we're going to end up with approximately 38 people. Now remember, initially, because in this model, nobody dies and nobody comes in, right? I mean, it's a closed population model. If you add all the derivatives, you get 0, which means that the total population never changes. You always have 102 people in total. 38 people essentially are those who never got the infection. Like I said, eventually the final size of I is 0, which means the recovered class, the final size of the recovered class is going to be 102 minus 38, which is 64. So in this scenario, we have 64 infected people. Okay, so here is the punchline basically, right? If we take on face value, right, the answer to these two side-by-side exercises, which policy will be implemented if a government, let's say, has a choice between the two? Again, strip away the realism of the whole thing, This is a textbook exercise, basically, simplified as much as possible. But, in one policy, the result is that only 8 people will be infected eventually. In the other policy, we have 64 people infected eventually. Now, clearly, if you can't do both, right? If you have to choose one of the two, then the government will put the check mark on the vaccination policy because only 8 people will be infected. Now, here's the problem. That is all good for those who do get to be vaccinated, but not all are vaccinated. Nothing is perfect, even if they want to, right? So let's say the vaccination rate doesn't reach anybody. And in this case, of course, there is nothing to be done on the infected class, right? So those who are infected basically will have to, deal with the burden of the disease. In other words, by choosing this option, you deliberately removed the option of treatment, which is useful for those few, however few, who are infected. If you choose the treatment policy, of course, individuals have a chance for treatment, but overall for the society, it's a worse outcome because, of course, 64 people will be infected eventually. Now, here's a disclaimer. Obviously, you still have a better chance to, end up being healthy in the vaccination policy. Because, the probability is smaller that you're going to be the unlucky one in the 8 people infected. Okay, so probabilistically, it's a bigger chance for you to remain healthy in the vaccination case because only 8 people will be infected. But the fact of the matter is, when the decision is made, for example, to remove treatment, to not buy the treatment, again, assuming this simplified scenario, that is obviously against the interest of those few who are infected. So to add a little bit more realism, let's say the insurance will cover the vaccination and then not the treatment. Then the balance between the society and interest and the individual interest is that, yes, the insurance will work for most people, but you as an individual maybe have to think about how to save some money, or maybe, go to a different place, maybe even a different country, in just to secure, for example, a treatment if it's available, because you will know that if you're unlucky to be in the minority of people who are infected, then the policy implemented is not going to be with your interest in mind. So not with the individual, basically, but just with the society at large. And this is not for a malice, let's say. I mean, of course, the government or any public authority will have to make a decision based on society at large, right? It's just basically the responsibility of individuals to remember there are also things to take care of that, won't be available via the public policy, so to speak. So I thought this is basically an interesting textbook example to talk about. In the math modeling class, I have something similar. And, I ask about this, whether there's a moral dilemma of some sort if someone chooses between the two. Most of the time, of course, if vaccination and treatment are available, most of the time both are available. This is just an extreme thought experiment, more likely than a realistic scenario. But for the math, as a math exercise, I think it's still useful. So I'm going to end up with a short second part, just for people who may not believe if the answer is 8 and 32 or 38 in these examples. I'll just run these equations with Wolfram alpha, because again, these cannot be done by hand because they combine polynomials with logarithmic functions, so that's not possible to solve by direct methods. See you next time. All right, so we have the Wolfram alpha open here, and let's enter the first equation that we had for the model with vaccination. So actually I cannot use I because I'm going to call it J, because the I think I checked it before, and Wolfram alpha takes I as the complex number, the imaginary unit, so I can't use that. So 0.02 divided by 0.0003 times natural log of 2 over J. So again, let's call J instead of I. So when you actually do these equations with, let's see, solve, let's help Wolfram Alpha just a little bit more. So solve for J. One thing to keep in mind, yeah, I mean, sometimes you have more than one solution, but you always have to remember the conditions that you work on the problem. In our case, we had 102 people total. So even if you have extra solutions, only the one less than 102 will be acceptable. In this case, like you see, it's 8.17, the approximated format of the solution. And in the case of treatment, in that case, we solve for S first. Let's see, R over lambda was the same. This was changed to S over 100. And actually here, as you can see, you get two different values, 105.68, 38.6. And so I guess I took 38. I should have said 39, but you get the idea. I took 38 as the value for S, and it should have been probably 39. But 105 is definitely not acceptable because that's outside of the range. You can actually prove that the solution cannot go beyond 102. I mean, that comes from the way the model is established anyway. But the equation itself can have other solutions besides the one that are in the domain of our model. So 38.6 is the one feasible for our model. You have to always use numerical algorithms or programs like this because, again, this equation cannot be solved directly. So in conclusion, that's the main idea that I had with this example. We can actually go quickly into politics and lots of things unrelated to math. And I don't want to prolong the video for that, but if you actually go back to the past months, it will be an interesting thought. It will be an interesting exercise, in my opinion, to think about which policies. I mean, all policies, of course, had the interest of the bigger society, I suppose, as a whole. Wrongly or correctly, because sometimes these are also mistaken from the start in the sense that they may not be actually good for the society, although they are intended to be good for the society. But it's interesting to think about which one of these decisions, even if they are correct for the big society as a whole, they maybe are not correct for the individual. I keep on getting back. I had another video on the topic about the mask policy in the United States, which was discouraged in the beginning, and in my opinion, that's one of the biggest scandals. I mean, it should be one of the biggest scandals that came out of that, because although the lying essentially about whether the masks are good for the people was done under the intention to keep the supply open for medical workers. I'm not actually convinced. I mean, there's a big, of course, huge moral problem with that by itself, which I won't get into it right now, because you can essentially lie from a position of an authority as an expert that masks don't help, which is what they say. I mean, just one or two individuals that were supposed to recommend the measures for the policy. I'm not actually entirely convinced that it was good for the society as a whole, because if the mask policy was really, really aggressive to begin with, I think it would have been a good chance for the epidemic to be much lower in size, which means there wouldn't have been as many hospitalization, which means there wouldn't have been as many masks required, in the hospital setting. So because you would have just fewer infected people overall. But that is a subject for another day and not necessarily related to math. So I'll leave it at that.